Hello everyone, our topic is speeding up set intersections in graph algorithms using SIMD instructions. My name is Shuo. I'm a PhD student from Peking University. This is a joint work with my supervisor, Professor Lei Zhou, and Professor Jeffrey Xu. He is from the Chinese University of Hong Kong. As we know, graph is an expressive and flexible data model. A graph consists of a set of nodes and a set of edges connecting them. There are some examples here, including social network, citation network, knowledge graph, and so on. Due to the large amount of graph-based applications, graph computing becomes a crucial and hot topic. Instead of optimizing one specific graph algorithm, our work focuses on accelerating a widely used computing pattern, set intersection, to boost a group of relevant graph algorithms. The problem is, given two sides A and B, how to find the common elements in both of them efficiently. Here we take the triangle counting problem as an example. We say that three nodes value W from a triangle if there is an edge connecting each pair of them. Triangle is a base substructure of community, so counting or listing triangles is a fundamental problem in community detection algorithms. This is a snapshot of the triangle counting algorithm. The general idea is to intersect the neighbor side of the two nodes if they are connected. We find that set intersection is the most time-consuming step. From this table, we can see that the intersection step costs more than half of the running time of the three graph algorithms. We recognize triangle counting, click detection, and subgraph matching are primitive graph problems. Based on that, speeding up set intersection will result in accelerating a bunch of graph computing tasks. So let's see what can we do for accelerating set intersection. Here we give the pseudocode of the scalar version of merge-based set intersection algorithm. Suppose we want to intersect two solid sides SA and SB, collecting the common elements in SC. We iteratively compare two blocks of elements from SA and SB if the two elements are equal. We store this element into the result size SC, then increment the result size and advance the two pointers. Otherwise, we only advance the pointer of the set with a smaller element. Our idea is to exploit data level parallelism using SIMD instruction. SIMD instruction set is available in almost all modern processors, and modern processors has wider SIMD registers to support processing multiple data elements in parallel. For example, the SIMD compare equal instruction checks the equalities of the four integers in the two SIMD registers, and the SIMD shuffle instruction rearranges the four integers in the SIMD register. The basic idea is, instead of comparing the elements from the two sets one by one, we can compare them block by block in parallel using SIMD instructions. In our example, we use 128-bit SIMD registers, so we set the block size to 4. For wider SIMD registers, we can set larger block size. Then in each iteration, we load two blocks of elements from both sides and make all pairs comparison among the two blocks of elements by SIMD instructions. After collecting the common values, we compare the last elements of the two blocks and move forward the pointers with the block size. To further exploit the data level parallelism, we propose a compact BSR layout to represent neighbor node sites. We know that bitmap is a basic scheme to represent multiple elements in one integer, but bitmap has drawbacks. When the site size is small but the gap between the first and the last element is large, the bitmap becomes sparse. Sparse bitmaps result in sparse bitmaps may cost more memory space, and more importantly, it results in efficient intersection because of many redundant comparisons between two or zero blocks. In our BSR layout, we partition the bitmap into equal-sized pieces. Then each piece is represented by two parts, base value and the state trunk. The base value records the piece's index in the bitmap, and the state trunk is directly copied from the value of this piece. Then we can eliminate all zero state chunks from BCR to avoid the drawbacks of the bitmap. By combining the advantages of SIMD and our BSR layout, we propose a new algorithm QFilter to speed up set intersections, and this is an overview of our algorithm. At the first stage, we load 4 base values from the two BSR sets. Instead of comparing all the base values, we quickly filter out the redundant comparisons by batch checking strategy. And at the second stage, if there are some matched base values, we loaded the 4 state chunks from the two BSR sets, align them according to the matches of their base values and intersect them. Then we collect the matched base values and intersected state chunks and write back to the result. Finally, we advance the array pointers to the next iteration. This is our byte checking strategy. We gather 1 byte of each base value and scatter it to 4 different positions to a new SIMD register. Then we compare all 16 aligned byte pairs by one SIMD byte-wise compare equal instruction. Then the byte checking result is shipped to a 16-bit mask, namely filter, consists of 4 bit groups. Each group records the byte checking results from one element in BVA to the 4 elements in BVB. We clarify them into 3 types. Multi-hit group contains more than 1 true value bit. One hit group contains exactly 1 true value bit, and no hit group only contains false value bits. Note that a multi-hit group indicates false positive matches, since we only compare part of them. In such case, we need to check further bytes until no multi-hit group occurs. However, we find that multi-hit cases rarely occur, both theoretically and in practice. After byte checking, we align the potential matches by rearranging base values in SIMD registers and compare them completely. Accordingly, we align the corresponding state chunks and intersect them by a SIMD bitwise and instruction. Finally, we collect the result base values and intersect state chunks and write back the result to memory. By combining our BSR encoding scheme and SIMD algorithm, we achieve data level parallelism in 2 levels, and our approach outperforms other SIMD algorithms by 1 order of magnitude. Moreover, we find that node ordering impacts the performance of set intersection by affecting the compactness of BSR. So we formally define the graph reordering problem to optimize the compactness of BSR so as to reduce the number of combinations in set intersection. Unfortunately, we prove our graph reordering algorithm is strongly NP-complete, so we propose an approximate graph algorithm to find a better node ordering. Due to time limitation, we don't show details. Please refer to our paper if you are interested. Here are some evaluation results. We test 3 graph algorithms: triangle counting, maximal click, and subgraph matching, using 9 real graphs, and compare our graph ordering algorithm with the other 8 different graph reorderings. These 3 figures show the average speed up under different settings. We can see that our approach achieves 3.6 times speed up, 12.6 times speed up, and 3.3 speed up on the 3 graph algorithms respectively. That's all. Thanks for your attention, and I'm concerned.
We have time for 1 quick question. Yeah.
Does your algorithm scale with the vector leg? So if I give you the 16 line vector leg,
Yes, maybe if we have wider SIMD registers, we can intend the block size, and we can use the extended SIMD instruction set such as AVX2 or AVX 1512, the instruction set.
So it works with them, like have you tested it?
So the question is whether you have tested it with those wider sizes.
No, we just test 128-bit register and 256 welder register. But yes, we have.
Let's thank the speaker again.